Assalamu alaikum everybody. Today in this session we'll be discussing about computer arithmetic, and for that we will be discussing the number system and how it is implemented inside the microprocessor. So let's start. Okay, to understand the computer arithmetics, you need to have a grip on your number systems concepts, and especially how the number system works, and which includes the decimal number systems, the binary number system, which is the machine number system. Then we have hexadecimal number system. So these are some number system, and the octal number system. You should be able to understand how you can convert from one number system to another number system, and how to add in binary, subtract, and then we'll be discussing how it is implemented inside the microprocessor. Inside the microprocessor we have ALU, which is responsible for doing all the arithmetics, and there are multiple circuits which are used to perform different mathematical and logical operations. Today we are going to see some of them in detail, and this is the table which you should remember, because if you remember this, you will be able to do your processing and working and understanding the system faster. And here we can see that 4 bits in binary, which is a nibble, is representing a decimal digit or a hexadecimal digit. In this case till 9 it's decimal, then if you include all of them, then it's hexadecimal number system. So you should be able to quickly convert a binary nibble into equivalent hexadecimal. So that means 1010 is A, 1011 is B, and so on. Okay, so the ALU, which is inside the microprocessor, is the main circuit which performs the mathematical functions as well as logical functions and operations. So what is the input of that ALU is that we have some operands, and the results are also stored in the registers. So operands are basically the data on which any function is to be, or any operation is to be performed, and to implement that there are some control signals, and there are some flags which shows the current status of your accumulator. As we already know that we have in 8086 architecture, we have 4 general purpose registers, AX, BX, CX, DX, which you can use accordingly. But here just simply try to understand this, that we have a register which is going to show you result, and there are some registers which are going to hold the data, which is also known as operand, for the before the processing, and the flags will be telling you the current status of your accumulator. Okay, so ALU is going to perform the mathematics and logical function, and for that it is responsible for performing calculation on integers, as well as it can handle floating point, the real numbers. So a system is required to handle the numbers. Normally positive numbers are very easy to handle, but since we don't have any way of representing negative numbers, we need a system to handle this kind of problem when you are using sine numbers, like the numbers which have a negative sign. So there is a new system which we are going to discuss today, which says that if you want to represent negative number, there is a way of representing it in machine. So let's see how it is implemented. If you look at it, it's called sine magnitude system, and in which, if you have a 8-bit system, you can see here there are 8 bits. So the this right side is the LSB and the left side is MSB, the most significant bit and the least significant bit. So the number representing a sine magnitude system is that in 8 bits you have MSB. 1 bit MSB will be considered as the sine bit, and the remaining 7 bits in this 8 bit number will be considered as magnitude. So this sine bit will be used to tell the processor that it is a positive number or a negative number. For that, if this bit is 0, it means that it is a positive number, and if it is 1, then it means it's a negative number. So that means that if you have like 8 bits, so the maximum number that can be represented using 8 bit is, in positive it's going to be 127, and if you go to the negative side, then it's going to be negative 128. So the range will be from 127 positive to 128 negative. Okay, so there is a system in which we have seen that we will be using the MSB, the 1 bit MSB, as the sine bit to represent the sine numbers. Okay, in the normal binary format, if you write a number 1, it's an 8 bit representation, it's going to be 0000000001. If you look at this number, it's like same, it is just a binary 1 because it has only zeros on the left side. So for positive numbers, the representation is the same as for the unsigned integers, where the most significant bit is always 0. This is what you need to remember and understand, that if the most MSB is 0, then whether it's a signed number system or an unsigned number system, they will be same. But the additive inverse of a 1's complement representation is found by inverting each bit. Now what you do is, if you want to convert a positive number into a negative number, what you need to do is you need to take its first complement as step 1, and then a second complement, 2's complement, as a step 2, to convert a positive number to a negative number in signed number system. So 1's complement is, if you have a number 00000001 which is equal to 1 in decimal, so if you want to take 1's complement, what you do is you simply invert everything. 1 will be replacing the zeros, and the 0 will replace 1. This is the first complement. This step is called first complement, 1 complement. Then the second step is to add 1 to it. If you do this, this is called 2's complement. And what happens is that if you go from right to left, that is from this point to this point, you will see that you will get all 1's. Which is equal to FF. As I just told you earlier, that 4 1's equals to F. Remember the table which I showed in the beginning of this session, this video, and this is known as 2's complement. Okay, let's see another example. Here we have 0011 0110. So the equivalent will be 0011 is 3 and 0110 is 6. So this number, this binary numbers, is equal to 36. And next, what I want to do is to take the 1's complement, and for that what I will be doing is that I will be using 1, inverting 0 into 1 and inverting 1 into zeros. So wherever there is a 0, I'll put 1, and wherever there is 1, I'll put zeros. So This is the ones complement. Next step is to take the twos complement, and for that we know that we have to add 1 to it, and it will be coming out like this. I hope you know how to add numbers. So it will be this. So this is the twos complement, and if you look at it, it is 12, which is C, and this is 10, which is A in hexadecimal. So CA will be the equivalent negative number. Actually this CA is representing minus 36, so it's a negative number, and this FF is representing minus 1. I'm going to show it again later on, right? So this is it. Let's continue further. Okay, the advantage of using twos complement is that there is only one representation of 0. That means because 0 is 0, it is neither positive nor negative. That is why when you use twos complement and you have a 0, it will give you after twos complement a 0, which means that 0 is equals to 0, and every other number will be converted into a negative number. And this is the reason that we during the ranges we have, like I told you, 127 positive numbers, and then we have 128 negative numbers in an 8-bit system. So this is the reason, because 0 is counted only once. Anyway, let's look at this thing. For ones complement, let's suppose to make it easy, it's a 4-bit number. 4-bit number means you have you will be using the 3 bits on the right side as the magnitude and 1 bit on the left side as sine bit. So using that, we have numbers starting from 0, 1, 2, 3, 4, 5, 6, 7. So the maximum number that can be represented in a sine magnitude system is 7, and this 0 is representing that all these numbers are positive numbers. Okay, and if you look on the bottom side, you can see all the numbers have 1 here in the MSB, that it is indicating that it's a negative number, right? And it can also go till 7. Okay, but the problem is that we don't have any negative 0. So in twos complement system there is no number for 0, and there is a number which represents minus 8. So the range in 4-bit number system, a sine number system, will be from 7 positive to 8 negative. In 8-bit number system it is going to be 127 positive to 128 negative number, and if you go further, 16-bit, 32-bit, and so on, so the overall range will be increased. Okay, let's look at the addition of numbers in twos complement. Like if you look at this, there is a minus 7, this minus 7, you know that this 1 is indicating that it's the negative number, and 001 is the magnitude, so it's minus 7, and this is positive 5, positive because this is 0 here, and the remaining is 1010, which is 5. So if you add them together, you will see that 1 plus 1 is 0, 1 carry comes here, and then 0 plus 1 is 1, and 1 plus 0 is 0. So we have 1 1 1 0, and if you look at in the terms of a sine number, you can see that MSB is 1, that means it's a negative number, and remaining is representing the magnitude, which comes out to be minus 2. So adding minus 7 plus 5 gives you minus 2, so it's correct. Next, look at this. Minus 4 is represented by 1101. This one is representing it's a negative number, and this 0 is representing it's a positive number. It's a positive 4 and it's a negative 4, and if you add them together, you will get this 000, and there is a bit, the 5th bit, which is 1, but since we are in the 4-bit system, so we will be only considering the 4 bits, and the fourth bit is 0, which is indicating it's a 0. So minus 4 plus minus 4 is 0. And if you look at this example, 3 plus 4 is 7. This is straightforward. 0, both the numbers are positive numbers, so 1 1 1 1 1 1 gives you 7. The fourth case, 1 1 0 0 is minus 4, as we have seen here. 1 1 0 0 is minus 4, and 1 1 1 1 is FF. Remember, I told you F and F is minus 1, so if you add them together, you will get minus 5. Minus 4 minus 1 is minus 5. There is a fifth bit which we are going to ignore in this case because we are in the 4-bit system. Same is the case here. 5 plus 4 is 9, but there is an overflow because in 4-bit system you can only have from plus 7 to minus 8. So 9 is not there, that is why it's an overflow case. And here same is the case here. Minus 5, minus 7 and minus 6 gives you minus 13, which is again indicating that it's a overflow case for the 4-bit. But if you are doing this in the 8-bit system, then it won't be a overflow because the range increases with the number of bits. Okay. The last thing which we are going to discuss in today's session is the multiplication of unsigned numbers first, and for that we need to understand the basic terminologies, and the basic terminologies are simple. The first number which is to be multiplied, it will be called multiplicand. The other number by which you are multiplying, it will be called multiplier. Then there will be partial products depending on the number of bits of the multiplier, and finally you add them up and you get the final product. So this is a binary multiplication, and it's almost same like we do in decimal. The same multiplicand, multiplier, then partial products, and then the final product. Okay, the process of multiplication is very simple, which can be understood using this flow chart. In here, as you know already, that we have multiple registers, the general purpose register, which can be used as your want them to be. So what we are going to do here is we are going to use some registers, and we are going to name them M multiplicand, Q multiplier, C and A will be holding the values of 0 which are counting, and the result will be in A and Q. Okay, so what happens is that, as we know already, that when you multiply by 0, the result is 0, and when you multiply by 1, the result is the other value of multiplicand. So simple terms, what you are going to do is you are going to check whether the value in Q0, that is the multiplier, is 0 or 1. If it is 1, then what you are going to do, you are going to add the value of A and M and transfer it to CA. If it is not 1, that if it is 0, then you will just straight away go to this step in which you are shift writing the C, A and Q, and you are decreasing a count of 1. As I said earlier, what happens is that once one cycle is completed, you generate one partial product, and then you goes to the second bit. So this is how it's going to work. I'm repeating it again, that when Q0 is 1, you will perform addition between accumulate A and M, and then transfer the value into A and C, the registers, and then you will be shift writing and decreasing the count until the count is 0. If the count becomes 0, that is, if you have multiplier with 4 bits, so there will be 4 cycles. Multiplier with 5 bits will give you 5 cycles. So this decreasing count will make sure that you perform that many number of cycles, and if it becomes 0, you will proceed to terminate the program. But if it is not 0, then obviously you are going to go back and back until you are 0. This makes sure that all the number of bits the multiplier has will be executed and proper result is produced. Okay, where we have this registers M, and then shift and add logic, we have multiplier and Q and A and Q will have the result. So this is simple block diagram, but I'm going to show you this example. Okay, first I'm going to tell you what are here. We have M register, which is holding the multiplicand, the Q register, which is holding the multiplier, and A will be holding the result with Q also. So these three are to remember, and if you look at M, we have 1011 as the initial value, Q has 1101 as the initial value, and A is 0000. So what happens in the first step is that we know that we'll check Q0, and Q0 is this bit. This bit is Q0, that is on the right side. And what, remember, in the flow chart we know that we are checking it for 1. If it is 1, what we are going to do is we are going to add the value of M to A. Because it is 0, what we are going to do is we are going to add this to this, and the A is all zeros, so 1011 will give you this 1011. Okay, then this is addition during the first cycle. After the addition, the next step is to shift right. For shifting right, you will be shifting A and Q, and you can see here this one which was coming from up there, this has come straight away. This is shifted out. This 0 is here, this one is here, this one is here, this one has come from here. Okay, so this is how shifting is happening. One bit is shifted on the right side, the cycle is completed. It checks whether the count is 0 or not. If the count is not 0, then obviously it's not 0 in this case, so it's going to move to the next step, and next step is it's again going to check 0, the Q0. Now this is 0. Remember, when Q0 is 0, we are going to skip the addition step and we will only perform the shifting part of it. So what we are going to do is we will just shift, and shifting, you can see here again that if you look at it, this 0 is lost, this one comes here, this one comes here, this one comes here, sorry, this one comes here, and this one comes in here, and same is the case that it moves like this. Okay, so the second cycle is completed. It will go and check the count, and when that count is again not 0, it will move to the third cycle. What it's going to do is going to check the Q0. Now it's 1, so what it's going to do, it's going to add M with A. So in this case, M is this and A is this, so these two will be added, and the result is this. So if you add 0010 to 1011, you will get 1101. After addition, the next step is shifting. For shifting, again, you know what happens. This goes out, this is this, and this is shifted this, and this comes here, and this comes here. I'm going to detail it, and a 0 comes in. See, so this is the third cycle. In the fourth cycle, because we had 4 bits in Q, the multiplier, so what happens here is that again we'll be checking what, the Q0, which is 1. That means we are going to add M with this, and if you add these two, you should be getting this value, and the fifth bit is this one. This is the fifth bit. Before it was not occurring, but now the result, after adding this and this, you get 10001. Then the next step comes in and the shifting happens. So shifting, again, this is lost, this moves here, 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 and this one moves here. So the final answer is 100001111, which is 8f. So the multiplication should be producing this result. Okay, finally, if you look at this, this was the first multiplicand, then second multiplier, then we have some partial products, and finally this was the answer we obtained there. And you can see that we have 1 0 0 0 1 1 1 1, which is 8f, and if you convert it, it is going to be 143 in decimal. So 11 multiplied by 13 will give you 143. So this proves that the method just shown of multiplication is a valid method for binary multiplication, and this is how it happens. In the next session we are going to continue this. I hope this has cleared many things which were confusing before, and I hope you have understood this topic. Thank you very much. Allah Hafiz.